Hello again, Mr. Dodd, working through the Calculus 1 using the limit definition of a derivative. Second learning target, this is where we're actually going to do the main thing in the learning target is finding those derivatives using that limit definition. The way we're going to do this is we're going to take the secant line problem that we did in D1 and we're going to generalize it. So instead of having specific x values like 4 and 6 like I used in the first one, we're going to use general x values like x and then this x plus delta x idea. Just to explain that a little bit, delta usually means change in. So if I start from x and then I add some width of a change, we'll call that width delta x, which is later going to be called the little pebble. X plus delta x is going to be my second x coordinate. So first x coordinate, second x coordinate. And then my y coordinates are just going to be f of whatever that value is. Okay. So as I go through, I'm going to use the regular slope formula to come up with a way of looking at this. And then we'll take the idea a little bit further. Remember, this is the point right here that I actually care about. And I'm just using these 2 points to get me there. So with that being said, if I take y2, that would be f of x plus delta x, and subtract off y1, f of x. So that's y2 minus y1 divided by x2 is x plus delta x minus x y1. That would give me m equals f of x plus delta x minus f of x divided by delta x. Okay. So that's going to be the general equation for a slope of a secant line as we go. Now, the idea from here is to take that general equation of a slope of a secant line and change it into the general equation for the slope of a tangent line. And the way that we're going to do that is by looking down here and thinking about our ideas of limits. So if I had a limit and I could squeeze that down as close to 0 as I could possibly get, that would allow me to make a better estimation. Said another way, if I were to, since I'm trying to find the slope of the tangent line here, if I were to get secant lines that are closer to this particular value, or choose points that are closer to this particular value to find my secant line, my estimation would get better and better. And if I could get really, really close, like this, I would be almost exact with my secant line using 2 points that are close. Now, if I squeezed this guy down all the way as close to 0 as I could possibly get, that would allow me to get the exact slope of the tangent line. So this is where the limit definition comes in. We're going to use this slope of the tangent line formula, okay, or slope of the secant line formula, and then we're going to take the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. Now, on the surface, this might not make a ton of sense, and you can see that delta x is a problem spot, because if I plugged in 0 using direct substitution for delta x here, I would end up dividing by 0. Delta x is one big chunk. I can't break it up, so I would replace that and I'd divide by 0. But there's going to be some algebraic things that we can do to get this delta x to cancel out, just like we did when we covered limits the first time. So with that being said, delta x, if we squish that down to nothing, remember it does actually work because limits care about what's happening really close. And if I can get close enough to 0, basically the word calculus is Latin for little pebble. And essentially the people who developed calculus, Isaac Newton, Leibniz, surely amongst others who didn't get the credit they deserved, basically what they said is if you can get close enough to 0, or if you can get to a place that's small enough, you can basically just ignore it. And then when they actually did the math, it ended up working. So that's where we're going at, or where we're coming from with this particular learning target. Again, I used the slope of a secant line formula in a general sense, then took the limit as delta x approaches 0 to write, and this is the exact, this will give you the exact equation for the derivative or the slope of the tangent line at any point amongst there. And the way we did that was by squishing this delta x down here all the way down to 0, which squished our points closer and closer to the point we wanted. And then once we get close enough, we can just ignore the difference.